Lesson 3, Portfolio Risk and Return. By the end of this lesson, you should be able to calculate the expected return and standard deviation of a two-asset portfolio, explain the concepts of covariance, correlation, and coefficient of determination, and calculate the covariance of a portfolio and the correlation coefficient between two assets. In the last lesson, you reviewed the concept of expected return and standard deviation for a single asset. This lesson will begin with a review of the expected return and standard deviation of a two-asset portfolio. The expected return of a portfolio is going to reflect, to some degree, the return of each asset. The amount that each asset contributes to the total return is a function of its weight within the portfolio. What is meant by weight? It's the percentage of the portfolio the asset represents. If in a $100 portfolio, $50 is invested in one asset and $50 in the other, then the weight is 50-50. 50% of the portfolio is made up of asset A, and 50% is made up of asset B. The expected return of a portfolio is simply the sum of the weighted returns of the assets. In this example, you are given two assets that are equally weighted in the portfolio, i.e. 50% each. Asset A has an expected return of 10%, and asset B has an expected return of 20%. The portfolio return is therefore 50% times 10% plus 50% times 20%, or 15%. As you learned last lesson, risk is the chance that you won't earn the expected return. As an investor, you want to know not only the return but the risk as well. Two statistical measures of risk are variance and standard deviation. The variance, referred to as sigma squared, describes the variability of historical returns around an expected value. Standard deviation, or the square root of variance, measures the average dispersion around the expected return in a more understandable way, i.e. 68% of the time, the actual return will be within one standard deviation of the expected return. 95% of the time, the actual return will be within two standard deviations, and 99% of the time, the actual return will be within three standard deviations. While expected return is a weighted sum of individual returns, the sum of the weighted variances or standard deviations of the two assets is not a sufficient measure for portfolio risk. The reason is because weighted variances don't consider how the assets move relative to one another, i.e. covariance. This is an important concept that will be investigated throughout this lesson. The standard deviation sigma for a two-asset portfolio is calculated as the square root of the following summation. The squared weight of asset A times the variance of asset A, plus the squared weight of asset B times the variance of asset B, plus 2 times the weight of A times the weight of B times the covariance of AB. Notice that the first and second terms in this summation are simply the square weights of each asset's variance. The third term is what accounts for how the assets move relative to one another. This term is 2 times the weight of A times the weight of B times the covariance of AB. So what is covariance? When you look at the risk of a two-asset portfolio, you need to consider how the two assets move relative to each other. Covariance is a statistic that explains that relative movement. So how do you calculate that? First of all, think back to last class when you learned how to calculate the variance of a single asset. That calculation required that you subtract the expected return from the scenario return. Square that difference, and then multiply that by the scenario probability. You did that for every scenario. For example, the bull market, neutral market, bear market. The sum of these weighted differences, i.e. the scenario return minus the expected return times the probability of its happening, equal the variance. The calculation for covariance is somewhat similar because you once again consider the probabilities, the expected scenario returns, and the overall expected return. However, this time you consider both assets A and B simultaneously. Consider the equation for covariance. The covariance of asset A and B equals sigma, or the sum of the scenario probability, times the scenario return for asset A minus the expected return for asset A times the scenario return for asset B times the expected return of asset B. You see that once again you multiply the probability of the scenario occurring times a measure of deviation from an expected return. However, for covariance, you don't square the difference, but rather multiply that return difference of asset A times the difference for asset B. By doing this, you consider how they move together. Once you do that for the first scenario set of returns, you do it for the remainder of returns and then add them up. Let's now work an example so that the process becomes crystal clear. Consider the following table of information. You notice that there are three scenarios: a bull market, normal market, and a bear market. The probability of each scenario occurring are 30%, 50%, and 20% respectively. Asset A has an expected return of 14.5%. This expected return is calculated as 30% probability times a 30% scenario return plus 50% probability of a 15% scenario return plus 20% probability times a 10% scenario return. Asset B's expected return is 8.1%, and it can be calculated using the same methodology as just explained for asset A. Let's calculate the covariance of assets A and B. First, you calculate the bull market covariance component as 30% scenario probability times a 30% scenario return for asset A minus its 14.5% expected return times a minus 8% scenario return for asset B minus its 8.1% expected return. The product of these three numbers equals minus 0.749%. Using the same methodology, the normal market covariance component is 0.008%, and the bear market covariance component is minus 1.563%. Adding the three numbers results in a covariance of minus 2.32%. Note that the negative covariance number implies that the assets don't move together. Stated differently, the return of asset A is inversely related to asset B. A positive covariance number implies that the returns move together. Perhaps a more meaningful question is, how much do they move together? That question is better answered by another measure, the correlation coefficient. The correlation coefficient normalizes or standardizes the two asset relationship on a scale between -1 and +1. Normalizing a number on a scale is much easier to comprehend than visualizing and trying to grasp something like minus 0.0232 covariance. A negative correlation coefficient means the assets are negatively correlated. A positive correlation coefficient means the assets are positively correlated. You will learn more about this in a moment. The correlation coefficient, or ρ, is calculated with the following formula. The correlation coefficient of AB equals the covariance of AB divided by the product of the standard deviation of A times the standard deviation of B. Question. Given that the covariance between two assets is minus 2.32%, the standard deviation of asset A, sigma A, is 13.87%, and the standard deviation of asset B, sigma B, is 16.91%, what is the correlation coefficient? You now know that you can solve for the correlation coefficient by using the formula rho of AB equals the covariance of AB divided by the product of sigma A times sigma B. Inputting the variable data, you can find that the correlation coefficient is minus 0.9892. The correlation coefficient is extremely useful in describing the relationship between assets because it standardizes the relationship on a scale of -1 to 0 to +1. In this example, you discovered that the assets have a minus 0.9892 relationship. That is very near the negative end of the scale. Let's now examine just what the correlation coefficient scaling tells us. A negative correlation coefficient minus R means that if one asset increases, the other decreases to some degree. The chart on this slide depicts a scatter plot of returns for two assets. Note that the scatter plot is closely bunched. The plot reveals a linear relationship with a negative slope. The negative slope appears because asset A and B are inversely related, i.e., when asset A has a high return, asset B has a low return. If there is a perfect negative linear relationship where all the scatter plots end up on the regression line, then the correlation coefficient is -1. If the regression line of the plots reveals a negative slope, yet the individual plots are clustered above and below the line, then the correlation coefficient is somewhere between 0 and -1. It is important to note that holding two assets that are negatively correlated will reduce the portfolio's volatility. You will continue to learn more about optimal portfolios in the next module. A positive correlation coefficient, plus R, means that if one asset goes up, the other goes up to some degree. Note that the scatter plot on this chart again depicts a close bunching. However, this time the plot reveals a linear relationship with a positive slope. If there is a perfect positive linear relationship where all the scatter plots end up on the regression line, then the correlation coefficient is +1. If the regression line of the plots reveals a positive slope, yet the plots are clustered above and below the line, then the correlation coefficient is somewhere between 0 and +1. The closer to +1 the coefficient, the closer the relationship is between the two assets. It is important to note that holding two assets that are positively correlated can still reduce the portfolio's volatility as long as they aren't perfectly correlated. A zero correlation coefficient means that there is no apparent relationship between the returns of A and B. The scatter plot of returns is dispersed and no linear relationship emerges. The returns are random. A correlation coefficient near 0 implies a weak relationship. Because the assets don't move together, holding two assets that have zero correlation will reduce the portfolio's volatility. Consider the formula you just learned. Rho of AB equals the covariance of AB divided by the product resulting from sigma A times sigma B. If you know the correlation coefficient rho and the standard deviation sigma of assets A and B, you can easily solve for covariance. Covariance of AB equals rho of AB times sigma A times sigma B. Question: what is the coefficient of determination? The coefficient of determination is the squared correlation coefficient, rho squared. It measures the proportion of asset A's price movement that is explained by asset B. For example, if the correlation coefficient is minus 0.9892, then minus 0.9892 squared, or 97.9% of the price change in asset A is explained by the price change in asset B, i.e. systematic factors. In other words, 0.979 of the variation in asset A is explained by the linear regression line relationship, i.e. the correlation coefficient. The other 2.1% is due to other factors, unsystematic factors. The coefficient of determination will fall between 0 and plus 1. Practical application question: how do professionals in the financial planning community use asset correlation data? Answer: CFP and other professional financial planners know that when you combine assets with correlations less than plus 1, the asset's risk-return characteristics can offset some of the portfolio risk. That means you can achieve higher returns for a given level of risk. Let's work through a couple portfolio examples. First, you will analyze the risk-return profile of a one-asset portfolio. Next, you will discover the effect of adding a risk-free asset to the portfolio. Finally, you will analyze the risk-return profile of a portfolio holding two risky assets. Consider the following one risky asset portfolio. Based on the scenario probabilities and scenario returns shown, the expected return is 10%. The variance is 1.5%. And the standard deviation is 12.25%. You have already worked these calculations earlier. What happens to the risk-return profile of the one risky asset portfolio if you diversify 50-50 by adding a risk-free component? 50% of your total investment is placed in the risky asset, and 50% of your total investment is placed in the risk-free U.S. T-bill yielding 4%. The original risky asset, asset A, is now only 50% of the portfolio because the other 50% is invested in a U.S. Treasury bill yielding the risk-free rate of 4%. The return of the two-asset portfolio is simply the weighted average, 50% times an expected risky return of 10%, plus 50% of an expected risk-free return of 4% equals an expected return of 7%. The standard deviation of the risk-free T-bill is 0% because the actual return in each scenario equals the expected return. There's no variance. You know from earlier in this lesson that the standard deviation of a two-asset portfolio is equal to the square root of the following sum: the squared weight of asset A times asset A's variance plus the squared weight of asset B times asset B's variance, plus 2 times the weight of A times the weight of B times the covariance of AB. Furthermore, you know how to solve for covariance. Given the following information, you can calculate the risk-return profile of this two-asset portfolio. As you can see, when a risk-free asset is combined with a risky asset, the standard deviation of the two-asset portfolio is equal to the weighted standard deviation of the risky portfolio. Why? Because the risk-free rate doesn't have risk. the standard deviation of a risk-free asset is 0. Therefore, the risk associated with the T-bill is 0. The covariance is also equal to 0. Question: what happened to the risk-return profile when the risky asset was combined with the risk-free asset? Answer: the risk, standard deviation, of the two-asset portfolio was reduced by 50%, while the expected return was reduced by only 30%. The risk-return profile improved. Question: what happens to the risk-return profile of the one risky asset portfolio if you diversify 50-50? 50% weight to risky asset A, a 50% weight to risky asset B. Before calculating the risk-return profile of the two-asset portfolio, you have to know the expected return and standard deviation of risky asset B. Considering the following data. Based on the scenario probabilities and scenario returns, the expected return for risky asset B is 13%. The variance is 4.86%, and the standard deviation is 22.05%. The original risky asset, asset A, is again only 50% of the portfolio, but this time the other 50% is invested in risky asset B. As you clearly understand by now, the return of the two-asset portfolio is simply the weighted average. 50% times an expected risky return of 10% plus 50% of an expected risky return of 13% equals an expected return of 11.5%. Again, you will use the standard deviation formula for a two-asset portfolio. Inputting the weights, the standard deviation for asset A and B, and calculating the covariance by using the return data, you discover that the standard deviation is 4.9%. Let's take a moment to walk through these calculations. Calculating the first term, the weighted variance of risky asset A, is rather straightforward. 0.5 squared times 0.1225 squared equals 0.0038, or 0.38%. The same process is used to calculate the second term, which is the weighted variance of risky asset B. The third term is more challenging because you have to work through the covariance calculation. Sigma, or sum, of the probability for the scenario times the return of asset A in that scenario minus the expected return of asset A times the return of asset B in that scenario minus the expected return of asset B. The two scenarios in this case are the bull and bear markets. Their probabilities are 60% and 40% respectively. So, the first component is 0.6 or 60% times 20% minus the 10% expected return times a minus 5% minus the 13% expected return, or minus 0.0108. The second component is 40% or 0.4 times minus 5% minus the 10% expected return times 40% minus the 13% expected return, or 0.0162. Adding those two scenario numbers together gives you a covariance of minus 2.7%. Now that you have calculated the covariance of the two assets, you can determine the third weighted component. 2 times the weight of A times the weight of B times the covariance. Inputting the data into this formula, you get 2 times 0.5 times 0.5 times minus 0.027, which equals minus 1.35%. Adding the three terms gives you a portfolio variance of 0.24%. The standard deviation of the portfolio is the square root of the variance, or 4.9%. Question: what happened to the risk-return profile when the risky asset was combined with another risky asset? Answer: the risk, as measured by standard deviation of the two-asset portfolio, was reduced by 60%, while the expected return actually increased by 15%. The risk-return profile was greatly improved because of the way the two assets moved relative to one another. The coefficient of variation is one measure used to compare the relative risk-return profile of a security or portfolio. The following formula normalizes the return so that a useful comparison can be made. The coefficient of variation equals the standard deviation divided by the expected return. When risk is in the numerator, the lower the number, the better the profile is in terms of risk versus return. Similarly, if the measure of risk is in the denominator and the return is in the numerator, the higher the number, the better the return versus risk profile. Let's use the coefficient of variation to compare the expected return and risk profiles of the three examples you just examined. Based on the analysis of expected portfolio return and risk, the following coefficients of variation are calculated. For the standalone risky asset, the coefficient of variation is 1.02, or 9.17% divided by 9%. For the risky asset with a risk-free asset, the coefficient of variation is 0.71. That was calculated as 4.59% divided by 6.5%. Combining two risky assets, the coefficient of variation is 0.42, or 4.9% divided by 11.5%. Which result is better for the investor? Based on risk-adjusted returns, the two-asset risky portfolio offers the investor the best return for the level of risk assumed. The worst portfolio on a risk-adjusted basis is the single risky asset. That makes perfect sense based upon our study about the positive effect of covariance. In this lesson, you learned about expected return and standard deviation of a two-asset portfolio, the concepts of covariance, correlation, and coefficient of determination, and the coefficient of variation.